To start today's seminar, and the speaker is Roger Moser from Bath, and he will speak about, I don't remember the title, but it contains vortices and Landau-Lifshitz Gilbert equations.
Yes.
Please welcome.
Thank you. And first, just so that you know what to expect, this is a PDE rather than an SPDE talk, so it's about a deterministic model, and it's joint work with Matthias Kurzke from Bonn, Christoph Melcher from Aachen, and Daniel Stern from Minneapolis. What we studied is a model for the magnetization of thin films of ferromagnetic material, and in this context, in some situations, you observe topological singularities in the form of vortices, and so this is what we studied. There's some mathematical connection here to the theory of Ginzburg-Landau vortices, which are relevant in the theories of superconductivity and superfluids. And the connection is that in both cases you have an underlying variational principle, and the energy functionals are very similar. And for Ginzburg-Landau vortices, there's a lot of work has been done, and so it's natural to try to adapt this to the situation of ferromagnetism. But if you try that, then there are two problems. One is that the equation that you're interested in is a sort of hybrid between a gradient flow and a nonlinear Schrödinger equation. And for Ginzburg-Landau vortices, both types of equations have been studied, but with different methods, so it's not clear how to combine them. And the other problem is a geometric one, because in ferromagnetism you have a different geometric setting, and because we are talking about topological quantities here, this matters. So let me first say just a few words about the underlying energy functional. What we study are thin films, and we assume that they are so thin that they can be represented by a two-dimensional domain, omega. So this represents a thin film, a thin ferromagnetic film. And this has a magnetization which is modeled by a vector field on omega. And so this has values in R3, but under reasonable conditions it also has a constant length, and so after renormalization we can assume that this is just a map from omega into the unit 2 sphere. And for this M we then have an energy which I denote by E epsilon of M. That's 1/2 of the integral of grad M squared plus the third component of M squared over epsilon squared. Where epsilon is a material constant, and this is already a simplification of the energy studied in physics, and it's also rescaled in a way that is convenient for what I'm going to talk about later. We have two components, two parts. The first is essentially the Dirichlet energy of M. This comes from quantum mechanics spin interactions, and this favors a magnetization which is constant. The second term is that this comes from the energy of the magnetic field induced by this magnetization, and this energy has the property that it favors magnetizations which are tangential on the boundary of the sample. For a thin film, this means above all that it favors magnetizations which are in the same plane as the thin film, and this is why we penalize the third component here.
S2 is a two-dimensional sphere?
Yes, S2 is the unit sphere in our
So only direction somehow plays a role of the, because this is like a direction, it's not in intensity of.
Yes. And epsilon is a material constant, but it's also typically it's very small, and so we study the limit when epsilon tends to 0, hoping that we get an easier limiting theory which can still tell us something about the positive epsilon. Now let's first have a look at the L2 gradient of that functional, and for that purpose I first define the quantity f epsilon of m, which is the Laplacian of m minus m3 over epsilon squared. If we had a functional of this sort for a vector field into R3, then this would be minus the L2 gradient, but we have a target manifold S2, which means we have to change this a bit in order to get the L2 gradient. Namely, we have to take projections onto the tangent space of S2. And we can write this in the following form. So this gives rise to the L2 gradient, for which I use this notation. We can write this as m cross f epsilon of m, where this denotes the vector product in R3. And therefore, if this is a point on the sphere, then taking the vector product with this results in first we project this onto the tangent space of the sphere, and then we rotate by 90 degrees. So doing this twice will give the projection of minus f epsilon of m onto the tangent space of S2.
M3 is a scalar, or so in the definition of the energy you have M3 to the power 4.
This is the third component of M.
A third component, okay, thank you.
Then this L2 gradient appears in the so-called Landau-Lifshitz equation, which describes the dynamics of the magnetization. And this equation is dm by dt equals m cross the L2 gradient of E minus alpha times the L2 gradient again, where alpha is a positive constant. So this is called the Landau-Lifshitz equation, or sometimes called Landau-Lifshitz-Gilbert equation. And if we plug in this for the L2 gradient, then we get dm by dt equals minus m cross f epsilon of m minus alpha m cross f epsilon of m. And well, let me first say a few things about this equation. If we didn't have the second part here, then this would be an equation of the type of a nonlinear Schrödinger equation, because taking the vector product with m is like multiplication with I in the complex plane. And accordingly, in that case, the energy would be conserved under this flow. The second term here makes the equation parabolic. And if we have the full equation, then the energy is decreasing under this flow. And this is interpreted as a damping term. Accordingly, this is a damping constant, and I now choose a specific damping constant, namely 1 over log 1 over epsilon. There's no physical reason for this choice, but mathematically this is the most interesting situation, because if this decreases logarithmically in epsilon, then you expect a limiting theory where you have a contribution from both of these terms. Most of the things that I'm going to say also work for different choice here, but then you might have a situation where one of the two dominates and the other vanishes in the limit. So for this problem, we want to study the behavior of solutions as epsilon tends to 0. And before I say anything else about this problem, I'd like to compare it with another problem. Namely, one that we get from the functionals g epsilon of u, defined as the integral of 1/2 grad u squared plus 1 over 4 epsilon squared 1 minus u squared squared. And in this case, we consider complex valued functions on omega. So let's compare this with E epsilon. In both cases, we have a leading order term, which is just the Dirichlet energy. And we have another term that we can think of as a penalizing term. And it penalizes values of u or m away from a certain unit circle. In this case, the unit circle in the complex plane. In that case, the equator of the two-sphere. And we are interested in the case where epsilon is very small. So we have a large factor in front of this. Now, if epsilon is very small and the energy is not too large, then we expect that u or m will have values close to the unit circle or the equator in most of omega. But it may not be possible to satisfy this condition in all of omega for topological reasons. For example, let's assume that we study the problem together with boundary conditions, Dirichlet boundary conditions like this. So they are tangential to the boundary, and these are supposed to be unit vectors. we want to extend this into the interior of the domain, and preferably in a way such that we stay in this unit circle. That's not possible with a continuous extension, and so what we expect is that outside of a small region we will have something like this, but here we may have values far from the unit circle or far from the equator. So in this case we may have zeros of u here. In that case we may have a value close to the poles of the sphere. And this is in fact what's observed for which is typically observed for minimizers or solutions of other variational problems. And the size of this, let's assume it's a disk, then the radius will be of the size a constant times epsilon. In particular, if epsilon tends to 0, this will shrink to a point, and then we have a singularity here with a vortex structure around this singularity. The vortex is, of course, one of the most significant features of this limiting configuration, and so if we want to understand that, then we have to understand above all these vortices. And there are certain tools that help you to do that. In particular, we can locate the vortices using one of two quantities, the first of which is the energy density E epsilon of u, which is just the integrand of this functional, so 1/2 grad u squared plus 1 over 4 epsilon squared 1 minus u squared squared. And the other quantity that's useful in this context is the Jacobian of u, j of u, which is the determinant of grad u, or we can also write it as 1/2 of the curl of I u grad u, where the brackets here indicate the Euclidean inner product that we get when we identify the complex plane with R2. Now, it's not too difficult to see why the Jacobian is useful to study these vortices and to see this. Let's consider a disk in the domain. So that's the disk of radius r about x naught. Let's suppose we have x naught here, and then we may say x naught is here. So this is a disk in omega, and we assume that on the boundary of this disk the modulus of u is approximately 1. So in this picture the boundary does not intersect this region here. Then the restriction of u to this boundary is essentially a map from a circle to a circle, and therefore it has a topological degree. So let's give this a name, D. And near this boundary, we can always write U locally in the form rho e to the I phi. That may not be possible globally, but we can always do it locally. And then we can use this representation to calculate this quantity here. And it turns out that this is just rho squared grad phi. And so when we integrate the Jacobian of U over this disk, on the boundary this is approximately 1, so we have here approximately grad phi. Using this representation of the Jacobian and Stokes' theorem, we find that this is approximated by an integral over the boundary. The integrand is then grad phi ds. We have a factor 1/2 as well. And this is a geometric quantity, and in this situation it's just pi times d. So in particular, if no vortex is inside of this disk, then we will get 0. If we have vortices inside, then we will get pi times the combined degrees of all of the vortices. So that means knowing J means that we have very good information about the position and the degrees of the vortices. It's a bit more difficult to see why the energy density is helpful here, but let me try to give you just a basic idea of why this is helpful. Let's now assume that we have just one vortex inside this disk, and x naught coincides with the vortex center. So we would have this situation. Then we would expect that this is true not just on the boundary, but in fact in an annulus with outer radius r and inner radius c epsilon. And then for any number capital R between C epsilon and small r, we can consider the integral of grad phi ds over the boundary of the ball with radius of the disk with radius capital R, and this will always give 2 pi d. On the other hand, this is approximately the same as the integral of the modulus of grad u integrated over this boundary. And using Hölder's inequality, we get an estimate by the square root of 2 pi r times the integral of grad u squared, which in turn is estimated by the energy density. So we get an estimate from below for this integral, and when we integrate this over the interval, if we integrate this over capital R, then we also get an estimate for the integral of the energy density over the disk.
So this was all for the G, the second model.
Yes, yes. You would get something very, very similar for the other model, but let me concentrate on the G epsilon now. So that would be that would give an approximate estimate for this by there's actually the factor wrong here, and here you will get pi d squared log r over epsilon plus some small error term. And in fact, under additional assumptions, namely, if we have good estimates for the L2 gradient of the functional, and by this I mean just that the L2 norm of this doesn't grow too fast when epsilon tends to 0, then you can in fact prove then you can prove a similar estimate from above, and so you get so you know that this is approximately pi d squared log r over epsilon with an error term which is of lower order in epsilon. And so again, once you normalize this by the logarithmic term, you find that the energy density also gives you good information about the position and the degrees of the vortices. And if you have an evolution problem, and suppose you know the position and the degrees of the vortices at the initial time, and you want to find out how they evolve in time, then using these tools, you see that it's sufficient to keep track on either the energy density or the Jacobian of U. And this has been done for various problems in this connection. For example, suppose that we're interested in the gradient flow for G epsilon. So that's an equation of the form du by dt equals f epsilon of u. And if you're interested in the motion of the vortices, then it's a good idea to add a factor log 1 over epsilon here. because that gives you the time scale in which the vortices actually move. If we're interested in this equation, then it's a good idea to work with the energy density. And so let's first calculate the derivative with respect to time. That gives the divergence of du by dt grad u minus du by dt f epsilon of u where f epsilon is now not the f epsilon that I had before, but the corresponding quantity for the function as g epsilon, which is the Laplacian of u plus 1 over epsilon squared 1 minus u squared u. So far I haven't used the equation, but if we now plug in this here for du by dt, then we find that we find a new expression for this, and it's convenient here to renormalize because by this formula we're interested in the energy density scaled logarithmically with epsilon, and now using these two we find that this is the divergence of f epsilon of u grad u minus 1 over log 1 over epsilon squared du by dt squared. We have here a factor which tends to 0, so we can hope that this will play no role in the limit, and it turns out that this is actually true. And this is a nice term because we can rewrite it as follows. This is the divergence of grad u tensor grad u minus e epsilon of u I. I here is the identity matrix. By this I mean the matrix such that the entry ij is the inner product of du dxi du dxj. And then what I mean here is that each component of this is the divergence of a column of this matrix. And that means in particular that we can express this in terms of first derivatives of u plus the other stuff contained in here. And that's relatively easy to control, at least compared with something like this. And in particular, we can then use this to keep track of the energy density, and this way you can derive a motion law for the vortices. On the other hand, if we had not a gradient flow but a nonlinear Schrödinger equation instead, in other words, something of the form du by dt equals minus I f epsilon of u. Then it's not such a good idea to use the energy density, but it's much easier here to work with the Jacobian. Because if we differentiate this, then we get the curl of I du by dt grad u. And now, if we use the equation, then we can write this as the curl of f epsilon of u grad u, which is the curl of the divergence of grad u tensor grad u. And the second term up there disappears in this context because it's the curl of a gradient. So again, here we can express this in terms of something that's not too difficult to understand, and people have used this to derive motion laws for vortices also in this situation. But neither of these is the equivalent of the Landau-Lifshitz equation that I wrote down at the beginning. If we want the equivalent of the Landau-Lifshitz equation, then we have to consider something like du by dt equals 1 over log 1 over epsilon minus I f epsilon of u. And if you plug this, say, into this term here, then you get again a term like this, but in addition you also get a term where you have here I f epsilon of u grad u, and the same happens when we use the energy density. So if we want to use similar tools here, then we need to get rid of this I f epsilon of u grad u, because they are much more difficult to handle than this. And this is possible if we use both the energy density and the Jacobian simultaneously, and if we consider a linear combination of the two, which is chosen in a way such that the bad terms cancel each other out. So in this case, we use E epsilon of u and J of u simultaneously. And then we can derive a motion law for the vortices in this situation. I'm going to write down this motion law just in the easiest possible case, namely the case where we have one single vortex of degree 1. And then we get pi times 1 plus I A dot, where A is the position of the vortex center. And I identify the plane here with, I identify R2 with the complex plane here, so that we can multiply this with a complex number. And this is minus the gradient of a certain function W of A. So that's the situation for a single vortex of degree 1 at the position A of t. And W is a function on omega, which you can derive as a sort of renormalized limiting energy functional arising out of G epsilon, if you consider the right sort of limit. I think it's not, for the purpose of this talk, it's not so important to understand what W actually is, but you just get a function so that you have a motion law like this. So this is an ODE. If you have more than one vortex, then you get something similar, but then you have a system of ODEs instead of a single ODE. And this has also been derived independently by Evelyn Neo.
Just a simple question about this. Is it possible that this A hits the boundary? Or this?
Depending on the boundary conditions, yes, it may be possible. And in fact, our results only work as long as this does not happen. For example, if you have directly boundary condition, then you can show that it must stay within the domain. For Neumann boundary data, it's conceivable that it moves outside of the domain. Now, this can serve as a simple model for what we are actually interested in, but what we want to study is the Landau-Lifshitz equation. So let's now consider E epsilon of m instead of G epsilon of u. And it turns out that you can do similar things here. Of course, in this situation, you use the energy density that belongs to this functional. Which is this. F epsilon of m is now again the expression that I wrote down at the beginning, namely Laplace m minus m3 over epsilon squared. And we have to replace the Jacobian with something else too, and that something else is denoted by omega of m, and in this context it's called the magnetic vorticity. That's the inner product of m with dm by dx cross dm by dy. So angle brackets here denote the standard inner product in R3.
In the single vortex motion, is W the log of the lowest line?
No, it's more complicated than that. I think I cannot explain this now. So, but if you're interested, perhaps we can talk later. So these are the quantities that we use here, and then it turns out that for these we have similar formulas as for for the things that we studied previously. For example, if we differentiate this with respect to time, then we get the divergence of dn by dt grad m minus dm by dt f epsilon of m. And for omega of m, we get the curl of m cross dm by dt grad m. And if we compare this with what we had before, then we see that this is practically the same if you just substitute every quantity here with the corresponding quantity here. And if you remember that this is like multiplication with I. And in fact, the other calculations also work in this context. For example, we can represent something like this again as a divergence like up there. And so formally, it looks as if everything is the same. In this case, we expect then that we get a similar motion law. Again, for a single vortex of degree 1. The only difference is this 2 here, and this comes from the fact that the 2 pi here is a geometric quantity, namely this corresponds to the area of the upper of any hemisphere, whereas the pi here is the area of the unit disk. So formally things look the same, but if you want to make this rigorous, then you have certain problems. Some of these problems are technical, but one is geometric, so to speak. And in order to see what this problem is, let's again take a disk. dr of x naught in omega, such that on the boundary the third component of m is approximately 0. This means we are on the equator. We are approximately on the equator on the boundary of this disk. And then we want to study the integral of omega of m over this disk. So previously for j of u here, we found that this is approximately pi d, where d is the degree of the restriction to the boundary. Here, in order to work this out, we can use the fact that this is also a sort of Jacobian, but now it's a Jacobian for a map into the unit sphere rather than the complex plane. And so this is a geometric quantity as well. And in fact, it's approximately 2 pi d plus 4 pi k for some integer k. This is essentially the same as before, except for the factor 2, and that's the same 2 as in the motion law. Where is it? Up there. But this is new, and the k can be interpreted geometrically too, namely as the degree of M as a map into S2. Now, if we want to use this in order to understand the motion of the vortices, then we need to control this k here. That means we need to control the degree of M. The good news here is that since this is a topological invariant, it does not change as long as M remains continuous. The bad news is that this is not necessarily the case. That's because solutions of the Landau-Lifshitz equation can have singularities. And I'm not talking about the vortex singularities here, but this can also have singularities of a different type, even for a positive epsilon. And if that happens, then the degree not only can it change, but in fact at the singularity the degree must change unless you have two coinciding singularities such that the changes cancel each other out. So that means we either we have to find a way to rule out the singularities, or we have to study them in detail, and hopefully we can then control K. Now we have some results which show that we can rule out singularities under certain conditions. And these conditions are the following. First, we consider Dirichlet boundary conditions. Second, at the initial time, we only have vortices of degree 1. And the third condition is also something that is required at the initial time. At t equals 0, we have just enough energy to for these vortices here. More precisely, what this means is the following. Suppose that we prescribe initial data such that a certain number of vortices develop, say, at these points. Then you can show that such a configuration will asymptotically need a certain amount of energy. And we assume that the actual initial data will asymptotically have exactly this energy. And if all three conditions are satisfied, then we can show that these two remain true for all times. And then we can use that fact to rule out singularities, because it's known that a singularity needs a certain amount of energy, which under these conditions is just not available. And then we can control the k. In fact, in this case, it always vanishes, and therefore we then get the motion law rigorously. Of course, this immediately gives rise to the question, what happens if we have more energy than this? And that's an open problem. And there are other interesting open problems, like what happens if you modify the model in order to include the possibility of an external field. Or what happens if you study a model which in some other way is more sophisticated. But all of this seems to be rather difficult. Thank you very much.
Questions, comments?
What was the reason to take epsilon going to 0? What is
that it's a very small material constant. So the dimension of this constant is the dimension of a length, and this has the length of just a few nanometers, which is very small compared with the other length scale that you typically have.
My question. So in this case, you say you get the k equals 0, and so you got a system of ODEs. Can you prove global existence of solution of this ODE?
Yes. That's in fact not so difficult, because this W here is smooth, and it goes to infinity whenever you have a vortex approaching the boundary or two vortices approaching each other, provided that you have these conditions here. And so global existence then follows with standard methods.
And one more question in this respect is, you assume that all vortices have degree 1. And I guess that you also can have degree -1.
No, unfortunately not.
No, but in the theorem, but theoretically.
Yes, yes.
So, do you know something? What would happen that if the vortices have different signs, plus and -1? Or do you expect something if you don't know?
Well, I expect that in that case you couldn't rule out the possibility that two vortices collide. I would expect that at least as long as this does not happen, you should still get the same motion law, except that for negative vortices you would have a -I here instead of +I. But again, this is something that seems technically to be a lot more difficult.
Martin?
Yeah, so you derive the motion of the vortices in the limit, but then is there enough information in the location of the vortices to actually reconstruct?
There is, yes, once you know the position and the degrees of the vortices, you can reconstruct the limiting configuration completely.
Yes.
Seems that Neumann boundary condition is physically very important. So is it also an open problem?
Yes, it's also an open problem. Neumann conditions would be more natural physically. Dirichlet boundary conditions are not completely unreasonable, because the picture that I drew previously with tangential boundary conditions is actually something that's quite typical, and this is almost like Dirichlet boundary conditions, because you have just two choices. So this is not completely unreasonable, but Neumann would be better. And we can't do that either.
If the domain is three-dimensional, then we cannot imagine a tangential non-singular field on the boundary. Topologically,
yes.
This is impossible.
So in that case, you would expect vortices also on the boundary.
We have mentioned. So what's the main difficulty for Neumann boundary condition?
Mainly that we do not have Dirichlet boundary conditions give quite good estimates for the energy. And for Neumann boundary data, this is not so easy because energy can escape across the boundary.
I don't see more questions, so let us thank the speaker again.